Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems, and in today's class the learning objectives for this class are to understand how frames are allocated to processes when there are multiple processes competing for physical frames, how frames are divided between the different processes, and what is meant by thrashing, and what are the different ways in which you overcome thrashing. We were learning about demand paging and page replacement algorithms in the past few classes, and when you are looking at demand paging, whenever a page is needed, only then the page is brought into the physical memory, and when you are trying to bring the page into the physical memory, you need to have a free frame in the physical memory so that you can bring in the page. But if there is no free frame in the physical memory, then you need to look for page replacement. That is, you need to select a victim page and move that page outside and bring in the required page into that particular place. The other way, the other optimal thing that you can do is that you can have a set of free frames and try to bring that page into this physical frame and then select a victim page and move outside. And what will be the case when the physical memory is to be used by many number of processes? How do you allocate the frames in the physical memory to the different processes? So, say for example, if you have 10 or 50 free frames and if there are 5 processes, how many free frames will each process get? So, if you are how do you divide these 50 free frames among the 5 processes? There are different ways in which I can do this. This is what we learn first in this class. So, in pure demand paging, all the 50 will be in the list of free frames. You have 50 free frames and all the 50 will be initially in the list of free frames, and while executing a process there will be a page fault. Even for the first memory reference there can be a page fault, and when there is a page fault the required page is brought into the free frame, and if there is no free frame page replacement algorithm will be run to select a page which will have to frame, a page will have to move out and bring in the required page into the physical memory. And once this process terminates, the frames will be added back to the free frame list. There is another variant of this where the free frames are always available. You do not have to wait till a page is moved out into the secondary storage device and then to move in the required page. Rather than that, you have a free frame which is always available, and whenever you want to move in a page, you move it into the free frame, and then you can select some page which can be moved out, and that page can later be added to the free frames. Another is you must allocate at least a minimum number of frames for that process, and for each process you will have to allocate some minimum number of frames. And when you allocate frames to a process, and suppose in due course of time the number of frames allocated to a process decreases, then the page fault rates for that process will increase. So, that is when the process has got less number of frames, and if there is a memory reference to another new page, then page faults will occur, and when page fault occurs, that will call for page replacement algorithms, and then because of that page replacement will happen and page faults again will increase, and so on. And what we need to understand is that there is a minimum number of frames that needs to be allocated for each process. So, this depends on the architecture of the system, and it will vary from architecture to architecture. So, for a process to execute even one instruction, it may be needed for some minimum number of pages to be allocated for that particular process. So, this minimum number of frames that should be allocated for a process depends on the instruction set. So, it depends on the number of pages that this single instruction can reference. And say you have a machine in which all memory reference instructions have only one memory address, then there will be a need for one frame for one instruction and one frame for the reference. And suppose if you have instructions which need one level of indirect addressing, and then in that case you will need 3 frames for each process. So, the instruction will be present in one page, and then that will refer to a memory address that will be present in another page, and that in turn will refer to a page where you have the exact memory location. So, totally you will need 3 frames for each process, and that is for executing even one instruction you will need 3 frames. So, for a process in such a kind of a situation you need to allocate at least a minimum of 3 frames. And suppose if you have multiple levels of indirection, then you have more problems. Say worst case, what can happen is that even for a single instruction there can be a memory reference to one page which in turn can refer to another page, etc. and so on. Maybe it can touch even all the virtual memory pages. That is a worst case situation. So, what is needed is that it is required to place a limit on the number of levels of indirection. So, you can have say the maximum of 16 levels are allowed, and then you can maintain a counter and initialize the value of the counter to 16. Whenever a memory reference is being made for even for a particular instruction, then the counter is decremented, and if the counter goes down to 0, then you understand that it has gone for 16 levels of indirection and above that is not allowed, and you can terminate. So, you can maintain or you can maintain a maximum level of indirection for each instruction. And now, how do you allocate the free frames or the physical memory that is available between or among the processes that are competing for the physical memory? So, in this example, say if you have 100 frames and 5 processes, what you can do is you can give each process 20 pages. So, that is equally you are allocating the 100 frames among the 5 processes. This is called equal allocation. Suppose if you had slightly more number of frames, say you have say 103 frames and you have 5 processes, and what you can do is you can give 20 pages for each process, and remaining 3 pages or 3 frames can be added to a pool of free frames which can be kept in the list of free frames. And this is equal allocation, but the problem here is that each process can have a different size. That is, all processes need not have the same size. Then in that case, how do you allocate? There is no point in equally allocating the frames among all the processes when they have different sizes. So, and what can happen is that you may allocate more number of pages for one process. Say one process needs only 2 pages, but if you are trying to do an equal allocation, you will allocate more number of frames for that process. But some process may need say some 20-25 pages, but you will allocate only 20 pages for it, and 5 pages may not be allocated for the process. So, rather than doing equal allocation, what can be done is you can go for proportional allocation. So, in proportional allocation, what is done is that frames are allocated to the process based on the size of the process. So, see if you look at process Pi and say Si is the size of this particular process, you add up the sizes of all the processes to find out the total size needed. And suppose M is the total number of frames that are currently available. Now, how you allocate for one process is you allocate out of this total space, how much is the percentage or how much is the amount that is needed for this process Pi into the total number of frames. So, you can look at this example, that will be easier to understand. If you have M as the total number of frames, say 64 is the total number of frames that is available. You have process P1 whose size is say 10, process P2 whose size is say 127, and hence you can see that the sizes of both the processes are different. S1 has got a smaller size and S2 has got a bigger size, and hence you can allocate less number of frames for this first process and more number of frames for second process. So, A1 is allocated 10 by 137, and 10 plus 127 is 137, that is the total size into the number of frames, that is about 5 frames are allocated for this process, and for the second process you allocate around 59 frames. So, here rather than doing an equal allocation, what is done is you allocate space based on the size of the process. And what else you can do is that you can also include some priority. So, you can do a proportional allocation not just based on the size but based on the priority of the process. So, if a process has got a higher priority, then it gets more number of frames compared to a low priority process, or you can even have a combination of the size and the priority. And the next issue is that, say when multiple processes are competing for frames and you allocate some frames, some set of frames for each process, and now there is a page fault in one particular process. So, you try to bring in a page from the secondary storage device because there is a page fault for this process. Some page of this process is not in memory, you have to bring it from the secondary storage device into the main memory. And now what happens, where do you bring this particular page inside? Say there is no free frame in the physical memory, then you will choose some victim frame and then you bring that victim frame, the contents of the victim frame outside, and then bring in the required page inside. But now which victim frame will be chosen? Will that victim frame be one frame among the frames that is allocated to this particular process, or will it be a frame that is allocated to some other process? So, there are two options here. Whenever there is a page fault, you can select a frame one among the frames that is allocated to this particular process for replacement, or you can select for replacement a frame from a process with a lower priority than this particular process. So, it is called global and local replacement. In global replacement, you select a replacement frame from the set of all the frames, and one process can take a frame from another process in the case of global replacement. But in local replacement, what is done is that you select a frame only from its own set of allocated frames. So, in global replacement, you allow a high priority process to select frames from a low priority process. So, when there is a page fault in a high priority process, it will try to select a page from this low priority process and bring its page into the place where this low priority process's page was available earlier. So, because of this, what happens is that it will increase the number of frames allocated to a process, and because of that the process cannot control even its own page fault rate. Say for example, if it is a low priority process, some high priority process will pick its own pages. So, the low priority process cannot control its own page fault rate. So, the set of pages in memory for a particular process will now depend on the paging behavior of other processes. So, if the low priority process, even if does not have many page faults, but if a high priority process has got more page faults, it will pick pages from the low priority process, and hence the low priority process low priority process will lose pages. So, the paging behavior of one process will affect the paging behavior of another process, or it will affect the set of pages that are available for the other process. But in the case of local replacement, the number of frames that are allocated to a process does not change. So, each process will select only from its own set of allocated frames. So, because of that, the set of pages in memory for a process is affected by the paging behavior of only that particular process. So, this process may not be able to use other less used pages. So, because of this you see that the global replacement gives better throughput and it is the one that is commonly being used. So, now we move on to another topic called thrashing. So, what is thrashing? Say you have a process which does not have enough frames. So, I told you that you need to have some minimum number of frames that may be available, but it may not have many number of frames, some minimum number of frames is allocated to that process. And because of this, what happens when it does not have enough frames, the page fault rate becomes very high. That is, again and again there will be page faults and hence the page fault rate becomes very high. And if all the allocated pages are active, and then because of that what will happen is the page replacement will lead to more page faults. Suppose if you are using local page replacement, then in that case say 5 pages are allocated to this process and all the 5 pages are active and there is a need for the 6th page. So, you try to bring in the 6th page into the physical memory. So, you choose one among the 5 pages that are already available in the physical memory and move one of the 5 pages outside to bring in the 6th page. Now, what happens again if there is a reference to the page that you have just moved outside, then it will lead to a page fault. So, what happens again there is a page fault, again you will try to move one of these 5 currently that are available and again if it is an active page again and again you will get page faults. So, because of this what happens? It will lead to low CPU utilization. Why low CPU utilization? When you have a page faults, it will be necessary for bringing the page from the secondary storage device into the main memory, moving something from the main memory to the secondary storage device, and that will require disk IO and that will lead to some amount of time to service the page faults and hence the CPU utilization becomes less. So, now what the operating system thinks? It thinks that the CPU utilization is less. So, maybe there are not enough number of processes to execute and hence the CPU is not utilized. And hence what happens? The operating system will try to increase the degree of multiprogramming. So, it will add what is degree of multiprogramming? It is the number of processes that are kept in memory at a particular time. So, in increasing the degree of multiprogramming, what it will do? It will add another process to the system. Now, already there are only less amount of space in the physical memory and now one more process is brought into the physical memory and because of this what happens? Again there becomes more and more page faults. So, now the system is now busy swapping pages in and out and the process is spending more time on paging rather than executing. And again the OS will monitor the CPU utilization. Again if CPU utilization is again less, it will increase the degree of multiprogramming. So, this goes on and finally at some point in time the process spends more and more on paging rather than executing and hence what happens? It leads to something called thrashing. So, if the currently executing process is needing more frames, it will take, if global replacement is allowed, it will take from other processes and when it takes from other processes, the other process will also fault and that in turn will take frames from some other processes and those processes will also fault and this will continue and high paging activity happens and it decreases CPU utilization further and degree of multiprogramming is further increased and this leads to thrashing. So, you see that look at this diagram, when the degree of multiprogramming is increased till some point in time the CPU utilization will be increased, but after that point in time suddenly the CPU utilization goes down when you increase the degree of multiprogramming. So, this is called thrashing or this period is called thrashing. So, how do you minimize the effects of thrashing? So, minimizing the effects of thrashing can be done by local replacement strategy. In local replacement, what is done? You try to replace only a page within the pages that are allocated to that particular process. And if you have to, you must provide a process as many frames as it needs at a particular time. So, at a particular time, a process may need some minimum number of frames. that depends on the locality of the process. So, this is supported by the locality model of process execution. So, what is this locality model? The locality is nothing but a set of pages that are used at a particular time together. Say for example, you have a subroutine, the process is executing a subroutine. Then while executing the subroutine, it will use the pages that are relevant to only that particular subroutine. So, that is called a locality. And when you are looking at a program as a whole, the program will be composed of several such localities. So, at one particular point in time, the process will be executing in one locality, and then it will move from one locality to another locality. And it is also possible that localities may slightly overlap. So, if the number of frames that are allocated to a process becomes equal to the number of pages in that particular locality in which it is currently executing, then there will be no page fault. Only after the process moves to another locality, then page faults will occur. That is, you can think of as this subroutine example. So, when a process is executing a subroutine, if you have all the pages relevant to that particular subroutine in the physical memory, then there is no page fault. And after completing execution of this particular subroutine, it may move to execute another subroutine, and only then you will get a page fault. That is, it is moved to another new locality, and you need to bring in pages relevant to that particular locality or that particular subroutine into the physical memory. So, initially you will have a few page faults. So, but why does thrashing occur? When the sum of the sizes of the localities of all the processes, say currently say 5 processes are using the physical memory, and each process will have its own locality or its own set of active pages. So, if you try to add up the active pages needed for all the processes, and if it becomes more than the size of the memory or the total memory size, then you get thrashing. So, how do we avoid thrashing? There are 2 methods that have been described for avoiding thrashing. So, one is called the working set model, which is based on the assumption of locality. So, here they define something called a working set window, which is denoted as delta. It is a fixed number of page references, and working set, that is the set of pages that are present in this most recent delta page references. And an active page will always be present in the working set, and if a page is not being used for some amount of time, then that page will be dropped from the working set. So, basically you can understand here that the working set is an approximation of the program's locality. So, currently the process is executing in one particular locality, and there are some set of pages that are active, and those active pages are called the working set, and you have something called a working set window, which refers to the last, say some n number of page references where you have this working set which are active. So, look at this example. So, this is the sequence of references that have been made, sequence of page references that have been made. So, reference to page number 2, 6, 1, etc. and so on for a particular process. At time t1, here you see that the last, you can look at here the value of delta is taken as 10. So, you look at the last 10 references, and you find that the pages that were active during the last 10 references are 1, 2, 5, 6 and 7. But at this particular time, say at time t2, the last 10 references have been made only to pages 3 and 4. So, here the working set at this particular time t1 comprises of 1, 2, 5, 6 and 7, and hence the working set size here is 5. At time t2, but the working set comprises of only 3 and 4, and hence the working set size is only 2 at this particular time. So, at time t1, it is enough to it is needed to have 5 pages for that particular process in the physical memory, but at time t2 it is enough to have only 2 pages for that process in the physical memory, because only 2 pages are active here at t2, but here 5 pages are active. So, what is done? The working set size for a process is found out, that is nothing but the total number of pages referred in the most recent delta references, and if delta is too small, it will not encompass the entire locality, but if delta is too large, it will encompass several localities. So, at time t1 in the example we saw that the value was you have 5 memory references that have been made and you have considered delta as the delta as 10. Suppose if delta was taken as only 5, then you may include only a few pages into the working set. But if delta is taken as say 20, you may unnecessarily have more number of pages in the working set and all those pages may not be used at that particular time. And if you take delta as infinity, then it will encompass the entire program will be included. So, the proper selection of delta is important. The working set size should be selected properly. If it becomes too small, then you will get more page faults. If you get too large, unnecessarily you will allocate pages which may not be needed. So, we see that the sum of the working set sizes of all the processes, that is sigma WSSI, can be found. That is the total demand for frames from all the processes. And if this value, if the sum of the working set sizes of all the processes or the total demand of frames is greater than small m, then it will lead to thrashing. What is the small m? It is the total number of frames that are currently available. So, if the demand is more than what is available, then that will lead to thrashing. So, if the policy is that how to overcome thrashing in this working set model, if the demand goes greater than the total number of frames, then you suspend one of the processes so that you will have more free frames and more space for the other processes. If the demand is much less than the total number of frames available, then you can initiate one more process. So, keeping track of the working set is difficult. There is a problem with practically implementing this working set model. So, for keeping track of the working set of a process, what you can do is you can have a fixed interval timer and a reference bit, and the timer can interrupt every 5000 time units. Say for example, if delta is equal to 10,000 references, and you can have 2 additional bits that is kept for each page. So, whenever the timer is interrupting, the reference bit is copied onto these bits. So, at some particular time you will have, say after 10,000 references, you will have a value in the reference bit. You will also have 2 values in these 2 bits that will refer to say 5,000 to 10,000 and 10,000 to 15,000. So, if from these bits you can understand which was referred to recently, and whenever a timer is interrupting, as I told you, you need to copy the reference bit and set the value of the reference bit back to 0. So, whenever a timer interrupts, you copy the reference bit onto these additional bits and the value of the reference bit is set back to 0. So, again after some more references, again you can copy and you can set back to 0. So, you will have in frequent intervals of time, you will have details about whether that page was referred to or not. So, if one of the pages, one of the bits at least in the memory is equal to 1, then it means that the page was referred to. So, what do we understand if the page is referred to? It means that the page is in the working set or the page is an active page. But this may not be completely accurate because you are only checking this in frequent intervals of time, and say you say you are referencing, or if you are interrupting maybe after say some 5,000 references. So, you will not know how many times that page was referred to within this 5,000 references, you only know whether it was referred to or not. So, the improvement that can be done is that you can have additional bits. So, as we had seen earlier in the additional reference bit algorithm, we can have additional bits to have more details about the history of the references, and it can also interrupt every 1000 time units rather than interrupting every 5000 time references. You can interrupt every 1000 time units. So, frequent interrupts are done, and hence based on that you get more details about the time or the number of times the pages were referred to. And the second mechanism is to have this page fault frequency scheme. In page fault frequency scheme, what you look at is you look at the page fault rate. Why do thrashing occur? Thrashing occurs because there is high page fault rate. So, what you need to do, you need to control the page fault rate. So, how do you control the page fault rate? You just keep measuring the page fault rate, and if the page fault rate is too low, then it means that there are very less number of page faults, then the process will lose a frame. So, if the page fault rate is too high, the process will gain a frame. So, if for a particular process, if the page fault rate is very less, then it means that it has got more number of frames than what it needs, and hence you can remove frames from that particular process. But if the page fault rate is very high, then it means that the process has got very less number of frames than that what it is needing, and hence it can gain a frame. So, just look at this diagram. If the number of frames is increased for a process, the page fault rate decreases, and if the page fault rate, you have two thresholds, an upper threshold and a lower threshold. If the page fault rate goes above this upper threshold, then it is too much of page faults for the process, and you increase the number of frames that are allocated to that process. If the page fault rate goes below the lower threshold, then it means that more number of frames are being allocated to the process, and you decrease the number of frames allocated to the process. So, we will summarize whatever we have learnt in this class. We learnt about allocation of frames, that is, given a set of frames in the physical memory, free frames in the physical memory, how do you allocate it among the processes that need these frames? And while replacing pages, there are two possibilities. You can go for a global replacement where you select a page from anywhere in the memory, or you can go for a local replacement where you select a page only among the pages allocated to a particular process for replacement. And then we learnt what is thrashing, that is, you have a lot of paging activity compared to execution, and you can overcome thrashing using the working set model or considering the page fault frequency. References, acknowledgement. Thank you.